the digital image processing subject. It is about utilizing local binary patterns for texture analysis. We have the outline, it's simple. We have the introduction, probable description, the description of the attempted algorithms, the results, and the discussion. Now, for the introduction, basically, you can read it in the screen as I speak. Basically, what we want to do is having a number of images which have a certain liquid-like component in them, which appears to be spreading. We wish to separate which portion of the surface is occupied by this liquid and which portion of the surface is occupied by the background or other elements. Of course, this can be applied in a larger range of topics, as we will see further down. You can also apply it to cells, for example. But for the problem at hand, this is what we're trying to do. There are some unique features. It's not as simple as just taking apart one half of the problem and the other. We will also see this below, where there are, for example, there isn't just background, there is some other element, some other unknown element, the background and the liquid, and we need to separate two of them from the liquid. Moving on, and the problem description, it describes what I just introduced, and it goes over the possibilities of certain algorithms. Now, ultimately, we focused heavily on LBP. However, other attempts and other possible optimizations can be made. While we use LBP, for example, we also use some degree of filtering, which makes it easier for us to add to the contrast of the liquid element and the rest. The first attempt is the simple binarization. For those of you familiar with MATLAB, you may know of this, but anyway, I'm going to introduce it. Binarizing an image simply means turning it black and white. As you can see in the picture here, this is the original image, and this is the binarized image. As we can further see, this isn't a very good approximate. For example, a lot of the parts that should have been taken by the white or the black are confused with each other. We're not looking to separate based on color alone. We're looking to separate based on texture, which is something more complex. For example, as we can see here, the color is some variety of gray that is very close to each other. However, the texture is different. Wait, let me zoom in a bit.
Okay, that's good. That's much better. Thanks.
Here, as we can see, this is a very smooth texture. It's entirely even, uniform, whereas this one is a bit coarser. That's why we need a more complex method that focuses on this problem specifically. That is why we use LBP. I'm going to zoom back out now. We will zoom in later, of course. As we can see here, is this. I don't think there's a need to zoom here. It's literally the same problem as before. This is why we move on to our real attempt, local binary patterns. Before we actually get to the point, it's best to describe and explain what LBP is. It's a texture operator which produces labels that are based on the neighbors of each pixel. By calculating these labels, it outputs the value as a binary number. It is a means of texture classification, of course, which is why we're trying to use it here. MATLAB is a very helpful method, extract LBP features, where you extract a portion of the cropped image and calculate those as LBP features. These are then applied to the rest of the image. We will see this in more detail below. This is basically how LBP works. Oh, right, one little mention here. The terms R and P. R is the radius in which we take the points, and P is the number of points. As we can see here, various different. Usually P is 8, almost universally. Let's assume we have. Yes.
P is the number of points, right?
Yes.
So you have if you have a neighborhood of 3 by 3 with radius 1, apparently.
Yes, it's 8.
You have the complete. Yes.
Almost every application uses this 8, but you can take any. Now let's assume this neighborhood. The pixel that we're focusing on is the one in the center here. And we have its neighbors, 0 value, 1, 1, 1. We assign them numbers. As you can see, they go in a clockwise order. And then we calculate them as a sum of binary numbers. For example, 0 times 2 to the power of 7, 0 times 2 to the power of 6, etc., etc. 0 times 1 times 2 to the power of 4, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. 16 plus 4 plus, you can see the calculation here, is 23. So the LBP value for this specific pixel right here is 23.
Yes.
As we can see here, we have taken the 4 in the center as a threshold. For example, the ones here are the values that are less than 4. The 5, 5, 8, and 7 are the ones that are more and have been translated to 0. For those of you who are familiar with image processing, this is an image known as Lena. It's very popular, but if you're not, it just as information, it's very well known. Of course, given the above example, we would have some form of conversion into a histogram. We see how the LBP values shift. For Lena here, we have this histogram, which makes sense since values at the edge and the center are different. Face recognition is actually one of the most efficient uses of LBP. It's not what we're doing here, but it can very well be used for purposes of face recognition. We take the histogram of each region and then we concatenate it into a larger one. The carpet and the bricks I've only displayed the carpet here, but there is also an example with bricks, are two of the main examples that MATLAB itself uses to display how the histogram works. This one is for the squared error. As you can see, the rotated bricks square error is much lower. This is with the rotated bricks. So basically the blue ones is the difference of LBP between the bricks and itself rotated, and the orange ones are between the bricks and carpet. This shows us that LBP can recognize texture regardless of rotation or shift in the image, because obviously the bricks are still the same texture, whereas the carpet is very different.
Yes.
This here is the part of the code. Here we take the squared error, the average, and we derive the score. Whereas here we use the extract LBP features. This is also in the appendix, but it's just code, something, the core of the problem. We then proceed, after calculating this, we proceed with another code to calculate the confluency. Now, I didn't talk about confluency before, even though it's been mentioned, because it's it's the key goal of the project, and I will be describing it here so we know what we're getting at. Basically, it's the percentage that the liquid applies in the image, percentage of the surface. You can see here, if the score is less than a certain value, we continue with the count. This is a threshold. At the end, we take for the circles that LBP creates. We will see what the circles are in a bit. We take the total surface, subtract them from the total, and that is the confluency. Here, this is one of the images with the fluid, which we mentioned before. It has been processed. As you can see, the texture in the middle is not as it was before. And it has had most of the exterior selected. This is what LBP does. It discovers that the texture inside and the texture outside are different, and therefore selects only one on the outside, will calculate one on the inside. Now, obviously, as you can see from the squares, from the circles, I'm sorry, in the center, there is a small margin of error. However, yes, given the total here and the fact that there are missing circles on the outside, this is negligible. We aim for a good confluency score, but it can never be perfect. That's normal. The threshold value was selected as 36, which is how we obtained the above image.
So Ari, you have found this one by setting an initial reference vector, right?
Yes. Let me scroll up just a bit. From utilizing this extracted LBP features, we set one of these, or maybe a difference of them, or an average. I used, for example, the average over 8 separate LBP features from different parts of the image that considered various features as the reference vector.
Okay.
Of course, some of them are going to give better results than others. I tried various combinations, for example, the first and the second, the first, second, third, and fourth, and so on, until I found the best value.
What was okay? So I see here in the code it's more clear.
The best value was actually, funnily enough, just LBP2. It seems I managed to find a really clear part of the texture and it selected them easily. Okay. I'll be displaying it below, not this one. This is an alternative example with cells. This shows us how LBP can be applied to other problems, not just the one with the confluency. For example, rather than having a single area that is well determined, like in here, we can see that the area is single. It's not one spot here and one spot over there. It's just a large block. Here we have multiple smaller areas, and still LBP performs very well. As you can see, apart from some small spaces between the cells, it calculates the confluency very well. Of course, this image is helped by the clean background. The original cell images have a very smooth background, which makes selecting LBP features very easy. Another attempt we made was using morphology. Now, this one didn't turn out very well on its own. However, it did allow for possible interesting application. It manages to take the entirety of the central part of the image and make it black. So this is for potential future work, how to apply morphology to this problem, but perhaps by extracting this internal texture, and then we can see the results. LBP, of course, as we said before, proved to be the most satisfactory. A number of alterations need to be made depending on the image itself, but nothing too big. The code is functional for almost any sort of problem of this nature that we have tested. We take the differences here. This is one example of the differences between 1 and 5, 2 and 6, 3 and 7, 4 and 8, but there are also other ones. For example, between 1 and 8, 2 and 7, and so forth, taken from the ends. The histogram for the square differences of the various LBPs. There are some huge differences depending on which areas you select. For example, 1 and 8 has this unevenness. This is 4 and 5, for example, a bit different. Notice the scale here, 10 to the power of minus 3.
4 and 5, do they belong to different regions, Ari?
Yes, they were selected from different parts.
Okay, like background and cell.
Yes.
Okay.
3 and 6, you can see here a huge difference again. And this one is, I think, the remaining one, 2 and 7.
So this histogram, it has, how many values does it have?
It should have the length of the vector, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that vector gives around 8 or something values. I don't remember. I can open MATLAB and check.
Okay, probably, I think it's like 10, probably.
10, yeah. Since there are 10 bins. I set the bin value to the number of vector elements. So
okay.
These ones are too small too. For example, the difference between 2 and 7, despite how it may look here, is 1 order smaller than these ones. These ones are 10 to the power of minus 3. This one is 10 to the power of minus 4, for example.
But the difference, Ari, do we read the difference in the y-axis or in the x-axis?
I don't between which ones?
For example, when we say the difference between the two different LBPs, are we going to read the difference in the x-axis or in the y-axis? So how do we read the difference?
I think we took the y-axis for this one.
Okay, so the difference between these two, for example, it's in one component of the LBP, the difference is 4. That's how I read it.
Yes,
no?
yes. Actually, 1 second, Professor. I think it's something else. It's this difference here, the squared error. This is the histogram of the squared error.
Let me think then just for a second, okay?
I labeled it difference, but it's as.
Okay, but this one then, this would be. I'm trying to understand this one because, I mean, I might have seen this a few times, but Okay, now I see on the x-axis you have up to 12 different values, and the y-axis of this first graph, can I see the y-axis of the first graph? This is 4, 5, okay, 5. This is
Uh,
very discrete, the differences are 5 or 1, 5 or 1 or 0.
yes, this may be because 1 and 8 were taken from relatively similar zones. I think one was pure background and one was pure background with a little bit of liquid.
Okay. But you know, Ari, I also was thinking also about this one. I'm not sure, but because I just don't remember, I can check it. But the difference that you find, it could be a scalar quantity. When
Uh,
you find that
yes, yes, yes.
LB,
It's the difference here is the squared error, so of course it's scalar. It's
so
just one.
difference between 1 and 5, but it gives just a number, 3, 5, 7.
I think since we're subtracting the vectors, it gives one number for each vector component. For example, each have 10 separate values, so the first with the first, the second with the second, and so on.
Okay, okay. Okay, that's good.
These are just some of the differences for this specific combination of different. There are others that I tested. I think one of them had even lower ones. This here is another image. This one was quite large, 500 megabytes.
Uh-huh.
The center is the liquid and the outside is the rest of it. The
Yes.
confluence score was 56, which 56% of the image is occupied by the liquid, which if we observe it is a fairly reasonable value. It's almost split half and half, a bit more than half actually for this one.
Yes.
And it has selected the rest of it with some with circles. As
Okay.
usual, there are some dark areas here.
Yes, yes.
In conclusion, to summarize, we were presented with the problem itself, used the LBP algorithm as a texture classification to extract the pixel neighborhoods, store them in a feature vector, which is the LBP1, LBP2, and so on. And then by using one of these vectors as reference, either one of the directly derived LBP values or some difference or average or something else, depending on our testing, we use them as a reference vector for the counting problem, which selects various circles in the image, takes the total surface area, and then gives us the confluence score. This is the appendix, the codes used. These are comments, of course. One example when we use just LBP1 as our reference, and one of the cell images. This was this code here. I'm gonna scroll to the end for now. This code here corresponds to the image. Let me scroll to it. This one.
Okay.
As you can see, even with, we could always optimize, of course, but even with a sample of the LBP, we can get a fairly good rate.
In fact, here, Ari, what did you use as a reference? Did you use the background as a reference or the cell covered area?
The background, professor. The reason for the cell image that I used the background was because the background was incredibly uniform. It was like a single gray. There was absolutely no texture, any other
Okay.
problem.
I see.
In
What
any of
about-
the image.
Okay, what about the size of the patch? How big was
I
it?
usually tried to take the biggest patches possible, which depending on the image varied a lot. For example, this one, it could have been a patch over this area from here to here. Usually a few hundred pixels per dimension. I think one of them was 200 by 200. Another one was 144 and 208.
I mean,
They varied a lot.
okay, so when you calculate, it looks like when you are doing in the for loop, when you are checking different regions in the image, you are changing the location by how much? By 200 pixels?
Let me check for the for loop here. 48 actually.
48, okay. So if this is 48 then, if you make this smaller, probably you get higher resolution around the edges.
Most likely, yes, it would be good. I thought that by taking it the largest possible would help. However, in fact, since I used 18 different images for this self-testing, some of the smaller ones actually had better performance. So by the end of it, I was taking them smaller.
Okay. Actually, it could be really good if you could insert next to this result the original image so that we can have a qualitative analysis.
Yes, that would actually have been good. I agree. I should probably add it. I could.
Yeah, I would suggest to add it because let's say, I mean, probably there could be some information right at the edge when you separate between the background and the structure. Okay, maybe we have some few percent of losses. It's fine, but it's good to we can compare them.
Always yes.
Yeah.
I'll add the images for this one and the others then, just in case.
Okay, and also I have another comment. Actually, you identify manually by looking at the structure of the background, and you conclude that it is more uniform. But what if you did not calculate the background and the beforehand? You just what if you calculate the LBPs vectors for all the image, okay, automatically? And then can you classify these vectors afterwards? And then find the area which corresponds to one vector and the area covered by another vector.
So you mean take them not randomly, just automatically, and then determine which ones belong to one class and which ones... That would be... Yes, that could be possible. It would be a classification problem, but given the differences in the image, for this problem, I think it could be easily done. Just take the vectors and put them into various classification algorithm.
Okay, because the thing is that you could, let's say, you don't go and look where is the, let's say you are blind to the type of the image, you have a black box or the image is given to you in a black box, and then what you could try is that you can have a sliding box all around the image, calculate the LBP vectors, and then assume that you have two classes, so that you can classify all these vectors in two classes, and one of them you make it black, one of them you make it white. You binarize it, This is,
for this one, that would for the cell problem, that could have actually been or could be useful. The liquid problem is another issue, since that one has more classes. Actually, we assumed originally that there were just two classes, background and liquid, but that wasn't the case.
Yes. Okay. And by the way, for the final exam in this course, we are not going to have a written exam in the class. It will be project based. Okay.
Okay, that's great, actually.
You find it positive, Ari? Okay.
Personally, I don't know about others, but personally, I would be more comfortable with the project in this time.
Okay, that's a good thing. But seeing this, it could be that okay. Thank you, Ledio, for your comment. So it could be that improving on the current projects could be one option to do for the final exam. Okay, or we can even change it slightly or give a different nice topic where you can learn or where you can practice something. Okay.
Yes, I could, for example, I could try and focus on the cells for the other project.
That's good. Okay, so what if you consider like the future step, Ari, like to do automatically classification of the LBPs without looking at the image beforehand, right?
Yes, that could be an improvement. I'll try to see what I can do with it.
What can be done? Let's think for a moment like this, Ari. So let's say you have a sliding window and you record. Let's say it would be something like this. You randomly inside the big picture, you select 12 regions and you calculate 12 LBPs and you start pairing these 12 numbers randomly. You can construct pairs like.
Yes, of course.
And then you can construct a histogram of the possible values, okay? And this histogram, probably you'll get some values around the zero, like you have a small Gaussian down there.
Yes.
Maybe that would be the difference between two backgrounds that look like each other. But,
right? Exactly, yes. When the histogram values are small, then we have the two LBPs are in the same class. When they're differences are huge, then they belong to two different classes, of course.
Yes. So that's a suggestion. Okay. Probably
Yes.
we could have a better idea, but then the first part of the code can do a categorization of what the LBPs are, and the second part of the code can run all of it.
Yes,
Yeah.
definitely.
Okay.
We could try that.
Yes. The other friends in the class? Do you have any other question for the presentation of Ari? If not, we can go to the next one.
Okay.
And Ari, thank you very much for the
I'm
presentation.
stopping this then. Thank you. Professor, should I add the PowerPoint presentation to the submission, or is it not necessary?
Edit.
Okay, great.
Include it, Ari. Okay, and also in the slides, which would make very clear for the listeners, would be really good if you could include the original image, how it looks.
Yes, I'm actually going to include it in the document as well, just in case. So.
That's good. Yeah. Okay, that's fine. Thanks again, Ari. And the next one, I can pick Igli. Igli, can you present?
Yeah.
Okay.
So next, I present the whole document.
Igli, whichever way you feel comfortable. If you open the Word document, fine. I mean, you can be the judge for a moment.
Do you see the screen?
Yes, we do. Yes, I do.
Yeah, all right. So my project is about object detection. Initially, I had it like object detection in the field of self-driving car, but lately I changed it.
Okay.
It's just object detection. So this is just a simple introduction that the aim of the project is about the autonomous cars. And I've started with some simple techniques first. Then I've made 3 experiments. But first, I'll just show one of the main problems is about detecting lane lines, to keep the car in the same line or to change lines. And I've used some of those techniques that we learned about Gaussian blur. First, apply a Gaussian blur. Then I've applied the Canny edge detection algorithm. And this is the lane lines. Now, the problem here is that I haven't defined the region of interest, because if you see the road is like curved. It's not like a straight road. And it's hard to define a region of interest, but you can see the lane lines detected here.
Yes.
Another technique, for example, is this one, perspective transformation. We're going to use this. We can use this later for traffic sign detection. As you can see, this traffic sign is like really bad viewing angle. It's a bit hard for a machine learning model to recognize this. So we can transform it. We can just pick in Python, for example, you can pick 4 points, and it transforms it in this pictures. In this picture, and this image is easier to detect for a model, for whatever training model that you have.
Okay.
Now the problem is that I automate this thing. Like I have to decide the points by myself.
So it is not automated.
No, it's not automated. Like you don't feed thousands of images and it's gonna find the perspective transformation. You have to pick the points by yourself.
Okay, thank you for clarifying this, because this is a question that might come up, the first one.
Yeah, this was the downside of it. Like I can't, right now I couldn't do it. Like I couldn't find a way to find those points automated.
Yeah.
Now, the first experiment is car detection using the LBP features. Should I explain the LBP algorithms? Ari explained it before.
Actually, let me think. No, I probably, if you have anything which you feel is slightly different.
No, it's the same algorithm. Okay, like it's exactly the same. It turns a region of 3 by 3 into a binary.
Yeah.
And this, here is the example. It turns it into 141.
Yeah.
Okay. So here's the data. I've got the data set. Data set is divided into 2 parts because it's going to be a binary classification.
Can I ask you something?
Yeah.
So let's say that you calculate the LBP and you select a 3x3 neighborhood, or which means that you have a radius of 1, and then you want to calculate in the image the LBP structure. So you want to see the LBP. Then what will be the highest intensity of each pixel?
Highest intensity of each pixel in the LBP image?
Yes.
Yeah, but it's gonna be this binary number. We calculate it.
Okay, but the Ari, do you have an answer, or anyone other in the class actually that are listening? If all of us, if we calculate the LBP for each pixel, what is the largest value? Or what is the smallest value?
The smallest value would be 0, and 255 is the maximum.
Yeah, that's good. Okay. 255 is the maximum. Okay, so what if we use...
If it's a 3x3. If it's a 3x3 kernel.
Good, yeah. What if it is 5x5?
It's gonna be like 2 to... let me think. 5 here once. 25 once. 2 to the power of 25.
Okay, that's closer. That's closer, I believe, Igli, okay?
It's a 5x5 kernel, so it's gonna calculate
24.
25. Okay, yeah, 2 to the power of 24.
That's good. So it looks like if we use a 3x3 neighborhood, probably if we want to show it as an image, the intensities will be unsigned integer 8 or u2 to the power 8, right?
Yes, so, at maximum 255.
Yes, so it will be very similar to unsigned integer 8 when we save the image. But if you have a neighborhood of 5x5, probably unsigned integer 8 type of variable would not be enough.
It needs a larger variable.
Yeah, so it would be maybe unsigned integer 16, or we have to calculate whether unsigned integer 16, it goes from 0 to 65,656, something like that, which is 2 to the power 16 minus 1. Because
we need the larger one, because if we have 5x5, we're gonna have like 2 to the power 25 maximum.
Yes, that's true. Okay, but this was a small note which we can think about it. But let's go ahead again.
Yeah, I didn't understand the question in the beginning, but yeah, the number is gonna be calculated from this here.
Yeah. Yes.
This binary is gonna turn it into a decimal. All right.
Good. Yeah. Thanks, Igli.
So we have labeled cars 1 and 0. 1 is a car, 0 is a no car, and we're gonna build a model later. We're gonna build a support vector machine model. I think most of us has done this support vector machine in the machine learning, machine learning course. Anyway, it's like a supervised learning model for classifying, not just binary classification. You can use it in multiple classes, but here I'm going to just use it into a binary classification. So what it does is find this hyperplane to maximize the margin between data points of both classes. And I've used sklearn to build the support vector machine model. And there's a function here, this one. There's a function that finds you the best params. You can give a couple of params. This grid search function finds you the best param for your model. You can give it a couple of params like this C and gamma. What this C and gamma is, C is the penalty for misclassifying the data, and the gamma is like the spread of the kernel. Basically, this radial basis function is a Gaussian kernel that we have done in the lecture.
Okay.
So these are the results of the training. Basically, I extract the LBP features of the image that we set here. Take the LBP features of the image and put it into a vector. for every image, and with those vectors, I trained the SVM model, support vector machine model. And here are the results.
Iggy, can you tell us what were the images again? I just missed it.
Car and no car.
Car and no car.
Can I
Okay.
show some of them?
Okay, so you use car and no car at the first part. Okay.
These are the images, like.
Yes, yes.
That's a 64 by 64 image. There was a data set. I have included the link. Where is the data set?
Yes, yes.
These are the images. From this, we calculate the LBP features and build the SVM model, support vector machine.
Yes, okay, that's good.
So here I've included the result with precision and recalls. Now precision means out of those predicted positive, predicted as cars, how many of them were actually cars? And the recalls mean that how many of the actual cars were classified as car by the support vector machine. F1 score is like parameter between precision and recall. It calculates like something like ratio between them. And this is another important part of the LBP features. Now here is the image, the original image. From this image, you can calculate the LBP features of the whole image. Actually, I didn't calculate the whole image because there was I find something like an error. But to generalize it, you just calculate the LBP features of the whole image.
Yes.
And then you feed those whole LBP features. You feed it to the model, and model is gonna try to find those 64 by 64 windows that we said before. That was the actual size of the images, if we remember in the data set. And
yes,
if somehow the models find the car, like let's say here it's not gonna find the car. So if it goes here, it's gonna find the car. There was a code I actually found in the internet to do it because it's a bit hard to do this in Python. But the idea is that if the model finds a car, it's gonna save those 4 data points into vector, and then later on we can draw a rectangle to the image.
Can I ask a question? Can I ask a question?
Yeah.
So this code that you did, when it does it, I see that the image is 600 by 1280, maybe.
Yes, I have resized it. Yeah.
Okay, but then how is it? Do you have a sliding window that is searching for cars?
Yeah, exactly. That's what it does. It goes. The windows goes exactly into each part of the image, calculate the LBP features of the whole image, and then we feed that to the model. If one of those images, it detects a car, it's gonna draw a rectangle.
Okay, and the next question is that I hope we can answer this fast, which is, what was the size of the sliding window?
64 by 64.
Okay, because this car, yeah, so the sliding window is 64, but it looks like the bigger car, it has a size of 100 by 100 approximately, if I'm not wrong.
No, this one here is resized. I've resized it into just, it's not, I think, yeah, you're saying about this one?
Yeah, for example.
It's just the resize, it's not the actual size of the image.
You know,
it's not the actual size
one. I mustn't this because when you have the search space, sometimes there are some parameters in object detection, which is like the region proposal network. It's called like anchor box sizes. If the anchor box sizes are not correct, you really miss what you are really going after. Okay, so that's why I wanted to.
Yeah, this one is 64 by 64. As you can see, it doesn't detect the whole car because the car is bigger.
Okay.
As you can see, one problem that I had here was that if I applied the whole image, the LBP feature is going to detect a car here. I don't know why. I tried to fix it, but I couldn't. Somehow it detects a car here.
Okay. Probably.
I apply the whole image. If I apply a region like this,
yes,
to 200, it's not going to find it. But if I apply the whole image, somehow it finds a car here. I don't know why, but
yes. Well, that's interesting because, well, even that case, Igli, if you do have such a case, include it in your report. It does not show that you are doing something wrong, but copy paste it here so that we can have a look, and then
I think I've. Oh yeah, to put the error. You're talking about the error.
Yes. I put the error here.
Well, I'll put it into.
Don't worry.
I don't know why.
No, it's good. But the thing is that the images that you have used, they are very low quality. 64 by 64. It's relatively bad or relatively low.
Yeah, it is. This you're talking about this one.
Yes.
Yeah, this one. That was the data set. It is a bit hard to find the car here. That's why it probably detects a car here.
Maybe it constructs the contours of a car. Maybe are constructed there somehow because the object detection contours is the most important feature. And probably
I should put the image of the error. I will run again the algorithm. It's here. LBP. I'll run again this one and I'll find the
problem.
Yeah, it's not here, but okay, I'll put it in later.
Okay, but thanks, Igor. Let's move on.
But here I've described it here about the problem. I've included that there was a problem with this technique.
That's good.
So I used another algorithm for feature detection. The model is the same. I've not changed the model. I just changed the algorithm for feature detection. I've used the hog features.
Yes.
Histogram of oriented gradient it is. So this is the algorithm of how it calculates the hog features, where we are taking this pixel here, which I've colored it with pink, and it calculates the gradient in x direction and in y direction. The gradient in x direction is 80, as I've put it here, and in the y direction is like 20. And from this it calculates the gradient magnitude. The magnitude of the gradient and the direction from those two, gradient x and gradient y. That's the whole. It compresses the whole image into these two params. And okay, the model, as I said, it was the same. Like I didn't change anything from the model, just changed the algorithm. It means like the data that was fed to the model is different from the previous one. And the hog features were way better than the LBP. If you can see here, it's like 0.96 precision and 0.97 recall.
Yeah, it's 10% better, it looks like.
Yeah, it's 10% better than the LBP.
That's really good. Yes.
So here I have now it's about the CNN, convolutional neural network to classify traffic signs.
Yes.
Okay. So this is the data set includes over like 50,000 32 by 32 images of traffic signs. The model is separated into 43 labels. That means that we have 43 different traffic signs. Actually, there are a lot of projects in GitHub about this traffic sign classification. It's a German data set about traffic signs.
Okay.
Okay, just to have a general idea about the data, 0, for example, means speed limit is 20, 1 speed limit is 30, and that's how we're labeled.
Yeah. Yes.
So for training, there are 34,000 images just for training.
Yes.
Should I explain the architecture of the CNN?
Actually, if we have a look, can we? If you can choose either in the code or sometimes there is a schema which are traditionally
here, or this one. I've included here as well.
That's good. Okay, we can have a look at this. Yes.
So this one is improved. First, it wasn't like this. Then I improved it. Okay. So it's as you can see, it's sequential. We're gonna build the model sequential. First is a convolutional. It's a layer about convolution to the 2D convolutional layer. This means that I have 32 filters, 3 by 3, and the
Kernel
input
size?
shape of there are 32 kernels, 3 by 3.
Yes.
The activation function is, this is the input shape. We're going to give the input shape of the images. The activation function is ReLU, rectifying linear unit, I think it is. Something like this. Yeah.
Yes, don't worry. Yeah, it's ReLU, ELU, they are, yeah.
Rectifying linear units, I don't know.
Don't worry.
Probably.
Don't worry about the,
The activation function.
Yes.
Then we add batch normalization. We're talking still to the first layer.
Yes.
And then we add max pooling. This max pooling is just for downsampling. Max pooling 2 by 2 kernel. This max pooling is for downsampling the image, because if we have a 32 by 32 image, in a 2 by 2 window, it's gonna select the maximum pixel.
Okay.
It's good for gaining some speed, probably.
That's true. Actually.
Yeah. Then I added this another convolutional layer with 64 kernels, 3 by 3, the same activation function, ReLU, same batch normalization, and same max pooling. It does the same. Then we flatten the data. Of course, here it's a two-dimensional image. Then we're gonna flatten it. After doing those two first layers, we're gonna flatten the data, and we're gonna feed it to another dance. This dance means another layer. This layer is gonna have 32 inputs.
Why is it going to have 32 inputs?
Sorry?
Why is it going to have 32 inputs?
You can have more than 32. It's not like, it doesn't have anything to do with image shape.
Okay.
You can have, it's just this 32. It's 32 inputs in the layer.
Yes. Okay.
And the final dance, this is important. This has to be exactly 43, because we have 43 classes.
Yes.
This one can change. You can put it into, you can have another input. You can have another input variable here.
Okay.
This has to be 43 because there are 43 classes, and activation function is sigmoid. Like, it's going to choose either it's 0 or 1. According to the probability, it's going to choose it's 0 or 1. This has to be sigmoid, or any other function that's going to give 0 or 1.
Igli, can you have a look at these vectors?
Which vector?
For example, no, because the last line, since you have 43 different traffic signs, you are going to get as an output, if the traffic sign is the third, probably you're going to get 0 everywhere, or 0.005 in every element. But if the traffic sign is the third one in line, which can be speed limit 120 kilometers, there you're going to have 0.9, which might indicate you have 90% probability to be this sign in this entry in this vector. Okay? So the output will be a vector where the highest value will be allocated where it has matched it with. So I'm just wondering, if you can output, you can print, let's say you want to see what a specific image input is, and I want to see the output vector.
You want to see the...
Yes.
Oh, yeah.
I mean, it might be also interesting for you and for everyone here. So,
yeah, here I have only the accuracy and the loss.
Yeah, this is accuracy and the loss. But anyway, later you can have a look at it.
Sorry?
Later, you can either have a look at it or, include it in the report, the vector.
Yeah.
And also,
I should also include the images change, right? The dimension of the images.
No,
after each layer.
Let me, and also, can I add something else, Igli? I do. To me, it looks like now you have two convolutional layers,
Yes.
right?
Yes, this is an improved version of the one that I sent.
Okay, but did the accuracy improve?
Yes, it didn't. It didn't improve much because I use only 10 epochs. Here.
No, okay. But
and if it is 0.91, let me show it to this one here.
Okay.
This one was like 0.87.
Okay, that's good. But Igli, that's really good work. But I was thinking if you can include also in the report, if you look at the word, it looks like initially the image size it is 32 by 32. Then after the convolutional 2D layer, the output of the first line of your code, it's gonna be 30 by 30. Okay. Then, but it's going to be 30 by 30 by 32 because it has 32 different layers because there are 32 filters.
I don't know why it's 30 by 30-ish.
Oh, 30 by 30, it is because when you have the kernel, the kernel 3 by 3, when it analyzes the initial vector, how can I say it? The output after a convolutional layer, it is a formula which is equal to the original width, which is, let's say, start with 32, minus 3, which is the kernel size, plus 1 divided by S. S is the stride. Stride is how much are you...
Nie meniu stride tu. Tu nie meniu stride.
It's a formula, okay? So I can write this on the board, but the kernel size, it can be... So what can happen is that you are using a kernel which is 3 by 3. You can also use a kernel which is 5 by 5 or 7 by 7. When you use a kernel which is 7 by 7, the stride or the jump from pixel to pixel, it can be plus 2 plus 3. Okay?
Yes. Okay.
If you have a jump of 2 or 3, the size of the input image will be decreased much more. But in this case, based that you have a kernel size of 3 and the stride or jump from pixel to pixel is 1, the output is going to be, after the first layer, you'll see an image which is 30 by 30.
Yes, I understand. I understand.
And you have the max pooling. Max pooling will make it 15 by 15.
Yes, 15 by 15.
Then you have a convolutional 2D layer again. This will make it 13 by 13 because you remove 2.
Yes.
Okay?
Yes.
So it becomes, what was it, 13 by 13 times 64. So now you have a three-dimensional matrix where the images are now downsized to 13 by 13, but you have a lot of filtered content. Anyway, so it's good to do this. So if
I understand.
Okay, that's good. But let's move on. Sorry, we spend a couple of time here. Anyone who is doing this kind of analysis would be really interested to have this discussion, but we can go to the next page. And I thank you for your patience, Igli.
Yeah, but this I just jumped a couple of pages because I went to the architecture, so I can explain the architecture better. This is like, here I've explained the initial architecture. The initial architecture did not have this one. This did not have this second convolutional layer. This one wasn't included.
Yes.
And the accuracy was 0.87 with 50 epochs. Which we mean that we're going to pass the data set 50 times forward and backward. The last one had only 10 epochs because it's going to take a lot of 10 epochs. I saw that the result was increasing. And
okay, that's good. Let's move ahead.
So this, I have plotted the training and validation accuracy and loss.
That's good.
As we can see, training is doing well. Validation not as good, but not as bad as well.
Okay, so validation is relatively important, but what is essential, whatever you do in the future, a graph like this, which shows the accuracy, this is what people are looking after, okay? So
yes, I didn't include this in the beginning.
But no, it's good that it is here. Even if you can calculate the loss, You can also plot loss versus epoch number or accuracy versus epoch number. But it's really good.
Yeah, it's versus epoch number. It's considered as 50.
That's good. Let's move ahead.
Okay. The last one is it's just gonna give. We're just gonna test the model that we just trained. We're gonna give a couple of images that hasn't seen before.
Okay.
The good of this data was that the images were separated. It was ready, so we just had to feed them to the network. Test images were separated. Training images were separated. And these are 9 random images plotted.
Yes.
It's gonna have the predicted class and the actual class. It just happened to be here that all 9 of them were correctly classified, but it just happened to be like this, but it's not like 100%.
Okay, we were lucky this time. Okay, that's good. It's good that you have shown what it is and what is predicted.
Yes, it is predicted 1. It is 1. If we go, okay, if I go like, here are all the labels.
Okay, that's good.
We can go there, check which label was. And this is the last part, which I already explained after the experiment. Experimented a little more with the CNN and improved the architecture of it. Added another layer, which I've explained before.
Oh, that's really good. Okay, that's good work. And I like the way that you made the Word document really compact with 3 different experiments. Okay, which was good.
Yeah.
Okay, thank you very much for all the presentation. But what if I ask you one question, Igli? Can you try to test this traffic sign model by having input an image and find the location of the traffic signs and what they are?
Find to draw like a rectangle, like the previous one with the cars.
Yes, to draw a rectangle with because if I think now, the problem of car no car, it was a 2-class problem, which is challenging. Okay.
Understand.
It's car no car. It's really good as a model, or even let me think for a moment. Even the car no car actually is you can test it there. But now I was wondering if you can go and find these traffic signs. It will be relatively difficult because you have 43 classes. You can even test it with less. But okay. And then I have, okay, what about this one, Igli? What if the images you use for training, what if the number of images was much smaller? Would you expect this accuracy?
I don't think so. It has to have many images to
train.
Perhaps it needs a couple of images to recognize if this is a class 1 or perhaps it wouldn't have that good accuracy.
Okay, and can I ask also what was the batch size?
I think it was. Let me check here. I think I've included the batch size. Okay, the batch size is 500 because there were like 50,000 images for training, and it has to be like around 500.
You know, for anyone who is really interested into this deep learning techniques, this might be interesting for all of us. But I was thinking about this one, Igli. The batch size of 500. You initially you had 50,000 images, right?
Yes.
Okay, I have a calculator now by bringing it from my cell phone, and you have 50,000 images, and I guess you used 34,000 for training, or 32. How much was it?
Let me check here.
It's not okay.
35,000 images were for training. So if we divide it by 500.
Yeah, I'm just saying. So 34,789, whatever. Now this one, if we divide this by 500. You have,
it's gonna be 70.
You get 70. How many steps did you use per epoch?
50 epoch. In the initial architecture, with one convolutional layer. 50 epochs with 500 batch size.
Yes, but how many steps did you use per epoch? Step.
What do you mean by step?
I don't. For example, I'm not sure how you run the code, but there is a number which is called step per epoch. When you run an epoch, there is how many times you are going to gather the images. So this 70.
Just one.
Uh-huh.
I think just one. You get 500 at one time. You feed it to the network. It gets back. That's how I think it works.
Okay,
50 times.
This is the number of epochs, and one epoch, it is classified as, in one epoch, one user has to have a look at all the images. So
yes, I understand. Yeah.
If you are picking the images 500 by 500 each time, probably you may need 70 steps.
70 steps to calculate the whole data set at one epoch.
Oh, is it what the step size that you use?
I haven't included any step size. That's why I wasn't confused at the beginning.
Okay, but what if you have a look at the code? Can you have a look?
This is
some keyword step. If you search, maybe it finds it.
Okay, this one here is. Yeah, this one here.
Okay.
It's the same code as this one.
Batch size is 500. If you scroll down a little more, let me think.
Yeah, this one. Batch size 500, epoch 10. It says epoch 10 because it's the latest architecture.
Yes. But I'm trying to pick up on relatively important information. For example, I see here that you have epoch 1. This goes epoch 2 is 34,799.
That's why I didn't understand like the steps, because that's how I knew it works. You give 500 at one time, and it goes back 70 times to calculate the whole data set at one epoch.
Okay, but that 70, I was expecting to see that written somewhere. I mean, in the code.
Yeah, that's the architecture. This one was the initial architecture which I found in.
I see. Okay, because traditionally, anyway, I said my question, so I was searching for it, but I could not determine it easily. Anyway, don't worry. So because wait a second, step. Can you scroll? But can you search Control F? Maybe you find this step. It's written somewhere. I'm curious more now. Step. If you search for. Two milliseconds per step. No, not this step actually. 2 milliseconds per step. No. Okay.
This is, yeah, but this.
Forget it. Sorry.
You can see there are few epochs. There's no steps. There's only this one here.
I get it. Okay. Yes.
Even before that, we have done this on other machine learning. For example, I don't remember using a step.
Okay. Because what if I wonder now if you run the same code and you use the batch size 5,000? Because to me it looks like I'm afraid that you are picking up 500 images at once and it goes to the next epoch right away without getting all of them.
No, it gets all of them. That's how the architecture. It uses Keras. Perhaps Keras does this. Maybe.
Okay. I'm just you have used it better than me, but yeah.
The size is 500 at one time, but it doesn't. It's not like it takes 500 and goes to the end and calculates the other epoch.
Okay. Or maybe this is the way it picks up everything. But okay, Igli, I thank you very much for all the presentation. It was useful. But I can also add a comment that the image size that is 32 by 32, they are not heavy for the memory, for RAM. If the images you are requesting from your computer to pick up 500 images at once. This is possible since the images are 32 by 32.
Yeah, I understand.
But if the image was like a little large, like 128 by 128, probably few computers would freeze if you are asking to pick up 500 images at once. Okay.
Yeah, we have to downgrade the these sites, not 500 at once, perhaps less.
So if you use, let's say, if you use a code when the images are cars and the images of cars was 64 by 64, probably you may go and decrease the batch size from 500 to a smaller number.
Yeah, of course, the RAM will probably fail. It won't have enough memory.
Okay. I want to ask the other students, anyone else has any question for Igli?
No.
Okay, Igli, I thank you again. And as a future task or a home assignment, you can consider this one. You actually tried this one using the cars, and probably that's enough. But you did it using only histogram of oriented gradients, which is good. But now with convolutional neural networks, can you find those traffic signs, or using convolutional neural networks, can you find the cars on a big image?
Yeah, I understand, yeah.
Okay,
yeah.
So you are counting cars using HOG, good, very good.
Yeah.
Let's see how the performance compares, okay?
With the neural network, with the convolutional neural network.
With convolutional neural networks, yes.
All right.
Okay, that's good. Thanks again. And the next presenter.
I used the CNN because there were like 43 classes, and I wanted to test not just binary classification.
You know, it's really good. It's really challenging with 43 classes. Accuracy with 43 classes, the accuracy might go down to 70%. Okay, and I was a little surprised with a single layer, with a single convolutional layer, with 43 classes. I mean, that's impressive. And but it's okay, I mean, which is good that it performs that way.
But it's also this data set. It's very used. You can see it in any GitHub repository.
That's good. But Igli, can you also compare what accuracies do the other find with the same data set?
Yeah, the first one was with the other data set. Use another data set.
Same data set, but other researchers. What have they found? The accuracy.
All right. Yeah. Okay. Yeah.
You know, it's always good to compare how they're doing the performance.
Yeah. Right. Right.
Okay, but everything is good so far. We can switch to a possible next presenter. Thanks again, Igli. On behalf of the class, we have here Nicolin. Nicolin, can you step in?
Yes, Professor. I'm with Enrit in group.
Okay, good. You can choose either way with whom you want to. You present first or Ernit first, but you can start.
We're going to present together.
That's good.
Okay. May I start?
Yes, please. Yes.
Okay, my name is Ernit, and today we are going to present digital holography together with Nicolin. I'm going to start with the introduction. What is digital holography? Digital holography refers to the acquisition and processing of holograms with a digital sensor array, typically a CCD camera or similar device. Image rendering or reconstruction of object data is performed numerically from digitalized in interferograms. Okay, next slide, please. Inline digital holography. The inline holograms is a record of interference between a plane reference wave and a scattered field from a 3D object. Digital holography, inline digital holography is mostly applied in imaging of imaging particle flows, such as holographic particle imaging velocimetry, two-phase flow visualization, flow cytometry, marine biological, and 3D imaging. Next, please. Here is a picture that illustrates us the idea of inline holography geometry. The straight lines in the picture represents the reference waves. When the electromagnetic waves, which is the reference waves, makes a collision with a particle, a scatter wave is created. Then the scattered waves makes a collision with the reference wave. They both fall in hologram because of the phase of those two waves changes. So when two waves falls in hologram, they interfere with each other, and it it have it they changes the altitudes, their altitudes. Next slide. Uh, exper Experiments with virtual holograms. They are 119 images were generated. Uh, Grayscale hologram image, the phase of the intensity fields, the module of the intensity fields. Each image was determined by these parameters: the z position of each particle, the x and y position of each particle, and the diameter or radius of the particle.
Basically, each 5 or 6 images were concatenated in order to compare the results of each of them. The first hologram that was taken from the sensor, the first hologram that was calculated was a complex image, and from that complex image we took the phase. So this phase gave us more information about the shapes in the image.
Okay.
From this complex image, the hologram was calculated as the sum of 1 plus the module in square of the complex image plus the real part of the complex image. And this was shown in grayscale for 6 images in the same image, in the same figure. We used subplot for this. The holograms also were shown in full range of color, and we also calculated for each group of 6 images the FTT and the angle of FTT transform for each of them. Basically, we were trying to find any correlation between the parameters that affected a single particle, which were the diameter, which stated the particle size, the x and y position, and z position.
Okay, that's good.
Okay, one particle test. In this test, only the effect of one particle was in one image. Only parameters, diameters, and the z position were changed. On 18 images were generated, and each 6 images were grouped to show the arranged results. Z position change. Here, as the Z increases, as we can see in the picture, as the Z increases, the circle representing the particle is increased. The circles of the particle created by the change in intensity of the radius. The distance between
Ernit, can you actually, when you present this, so far everything is good, but it's always good in this type of presentations to include the formula, because it's not difficult. You have taken numerical analysis courses, and you may already know how to convert an analytical expression, which involves integrals and derivatives. We know how to write it in discrete form or to write a code about it. Now, can you go 3 slides back to have a look what is Z for the other students in the class? Can you go to slide 3
Yes.
for a moment? Good.
Yeah.
Where is Z here?
Z is here, the straight line. Is
the distance?
The distance.
Is the distance from the object to the screen?
Yes. Yes.
Okay. So, and here, that's okay, that's good. So you have some light source. The light source is going through particles. Then from the particles, it's hitting the screen. That's good. Okay, let's move ahead.
I can say for the Z, if the Z is bigger, the farther away is from detector. So Z positions change. Here we can see the Z position changes. We have 4 pictures, and there are a Fourier transform of 4 images from the images of slide before. The change in the Z affects the Fourier transform by making it small.
So can I ask a question here? So these images are the Fourier transform of the previous images?
Yes.
Yes.
Okay. Okay. What if you could calculate an object right at the same position where it is? So in the previous slide, if you go back actually, let's assume that you just have an object right in the middle and find the Fourier transform of that object without the ripples. The ripples are these changing intensities, which are changing gradually. And because the hologram, it's always, if you have a single object in the center, it's like a sphere, okay? You go on Google Images, you search for a sphere, you see a white background, a black object, or the opposite, a black background and a white circle. And if you take the Fourier transform of that thing, it's going to be any one of these 4 objects that you have in this slide, okay?
Yeah, we have the Fourier transform of circles at the end of the presentation, I think, Professor.
Oh, okay. So
We should put them. Should we put them here?
No, well, if you have them in the end, it's fine. But I hope that we don't miss this important point that the holograms that we are getting are in fact the Fourier transform of the shape of the object. So you go in this course, we found the Fourier transforms of different images. We had pattern surfaces, we took the Fourier transforms, we found where the features were in the phase transform, etc. So by now, you are a specialist of how to calculate the Fourier transform of any random image. Now, calculating the Fourier transform of a sphere, which the sphere in this case, it is the obstacle. And these techniques which is included here, allow me just less than a minute, I'll just conclude. This holography that you are measuring, this is seen in microscopy. So when someone is using a microscope, you turn a light, the light, even in a ninth grade in biology course, you have a light source, the light is going through a sample, the sample is put on a transparent piece of glass, and on that piece of glass you have some cellular material or some biological sample or some tissue or any other thing. And then the light is passing through that object, and in the CCD, in the where you record the signal, you are recording the holography, in fact. Okay, so this is something which probably all of us have seen them a lot of times. Okay, it's a little different. I can explain in detail what is the major difference, but it's a very important, interesting factor which you already have seen it, at least in this course when we do imaging or image analysis. And you can also draw equivalence of what you see in these slides of this presentation with any course which is related to signal and systems. Okay, so this was just a small reminder that this is pure microscopy. Okay, we can go to the next slides. Sorry for the interruption, Nicolene and Ernit.
Here, for example, we tested the change in the size of the particle.
Okay.
As we see, it has a significant effect in the background. Basically, the more blue background means the less light intensity, I think. And
Okay.
the more, and also as the diameter of the particle changes, we can see that the particle is more in the center of the particle is more it's more yellow, let's say, which means
Higher intensity.
higher intensity.
Okay.
I think I have the whole, because there were 6 images, but
That's
we
good.
couldn't place all of them in the slide. Yeah, here are all the images.
That's good.
Yes, as we can see, for example, for 0.01, we have just it's all blue, so low intensity, but as the diameter is increased, the intensity of the center is also increased. But we also can see that the intensity in the background is decreased, so it become more blue.
Okay. Let's move ahead. 2 particle test.
Okay. Here we have the 2 particle test. On this test, 16 images were generated with 2 particles. For each particle, specific parameters were previously determined. Each parameter was changed, and each 6 images were grouped in order to make comparison between images. Next.
In the first experiment, we just created 2 particles that were on the same Z position, and we checked what will happen with the hologram if we keep changing the X and Y position of these particles.
Okay.
I think it's better if we see this image here, because we have all of images, because we generated 6 images.
Okay.
Yeah, basically we can see that as the particles come near to each other, we can see some lines. Here, for example, we have interference between the two let's say two circles formed by holograms, and we can see that these are straight. And as the particles come near to each other, these lines are more
Wider.
and as the more wider, and as the particles are far from each other, these are more thin. This means that as the particles are near to each other, we have more interference between them. We also check the face. Yes, it was the face of the complex image that was firstly generated, because these images were generated by a complex image, as said before. And here, for example, I think we can see a little bit more about the interference. I don't know if I can zoom it, but we can see, for example, that this is not a circle, but ca dessa Syria, professor.
Qual?
Que
Okay.
lidam para me pièce interferences.
Interference, yeah, I think you can call it interference, yes. Okay.
Here, as we can see by the picture, we have 2 particles which have different position in X and Y axis. The one that has bigger Z is further away from the detector, meaning that the figure is bigger. Interference lines in the picture are not straight. So, in my opinion, it looks like there is not much interference here. Okay, that's
okay.
Yeah, here we also tested the change in radius. But as we see, for example, when we change the radius, it mostly has affected the background. I don't know if we can check it here. I think it's this. Yeah, mostly it has affected the background of the image, so it doesn't has any effect in the interference.
Probably, Nicolini, it could be good if you can plot those graphs in 3D. There is in MATLAB it's like surf L.
Yeah,
surface L.
but it was very confusing. The image was very confusing.
Oh, okay.
But I can add it in the project report if it's necessary.
No, well, I guess if you have a look carefully, probably it might help you.
Yeah.
Anyway, so even in the presenting
because
data.
some of because there are a lot of circles here, so it's like a lot of up and down when you
Yes.
see the image.
Okay.
But I can try. I can try it.
That's good.
I can
Okay.
try it now, even now. If
No, it is good. No, let's go ahead. So you are adding more particles, I guess, would be the next
yeah,
step.
I are a little bit. Yeah, we have a lot. We tested a couple of more slides. The change in radius here, for example, we kept the same. Ernito, should I other possible? Here, for example, we kept the same x and y position for both particles. So let's say like this is the case when we have two particles in the same line and their hologram fall into the same place, and basically the difference between these two images is that here I think, just let me check. Here the particle that is near the detector, let's say, changes the radius, so the radius is increased, and we see that the background here is affected more, let's say. But here, for
Yeah.
example, the background hasn't changed much.
Okay, that's good.
Here we have change in Z position, as we can see from the pitch. In the pictures, we have different
Let me. I think
different coordinates.
sorry.
But
Yes.
can I also something, Aniti, in the codes, I think you have somewhere the wavelength. Do you have the wavelength?
Yeah, is the
Yeah, yeah,
wavelength of the light.
Yes.
Yes, it is.
Can you, what can be interesting is if you can check a little carefully how the shapes change as a ratio of wavelength over the size of the object. So if you change the radius of the object twice, and if you change the wavelength twice, what do you see? What could you see?
Yeah, in fact, we didn't thought about that, but it would have been very good if we changed the wavelength.
Because the interference patterns, they really depend a lot on the, what's the name?
Wave.
Yeah, on the wavelength, yes, and the size of parameter. But can you go to the last part where we can see the Fourier transforms of the objects?
Yeah. We also tested with free particles.
That's good.
Yeah, for example, here we can see like we have the middle particle at the first time is nearest from others, and here, for example, it's in the middle of these two particles.
Okay.
Here it's far further away. We also tested the radius change, and we also repeated the experiments for more particles. We repeated for 4, 5, 6, 5, 8, and 9 particles. Yeah, if we check in here, for example, yeah, these are random particles, and let's like where the background is more blue for when at the pictures when the number of particles is bigger, and also the particle radius, let's say, it's bigger.
Yes.
We also increase the number of particles from 10 to 35, and as you can see in here, it's
Yes.
yeah, we have a lot of interference. Yeah, we also repeat it from 50 to 100 particles.
Okay, then yes.
Yeah, I don't think we can learn anything from this image because there's a lot of interference.
Yes, that's true. Okay, let's go ahead.
Yeah, here we have the yeah we took the first Fourier transform of the circle, but
Okay.
changed its radius.
Okay.
It's 5, 10, 20, 40, 60, and 80, I think. Yeah.
Yeah. Okay.
This is another, as you can see in here, for example, we the Fourier transform. Yeah, this is like multiple rings, I think, Professor. So it's like you have a single circle in the middle, then you have another ring. Yeah, I don't have the original photo, but
But probably the original photo, it was just a circle in the center, right?
yeah, no, this is a circle that it's like rings.
Okay.
So you have a smaller ring, then a bigger ring,
Okay,
a
I
more
see.
bigger ring.
So then, is it possible to include in a better draft the original image and the Fourier transform? You know, so we can have both next to each other.
Yeah, I don't know if I have it here. Yeah, here I have it. This is the circle, but I don't have the circle. But this is just the circle that comes bigger. Yeah, these are the rings.
Okay. So you took the Fourier transforms of these images, right?
Yes,
Okay.
and it got these results, which are almost like similar to this one. Yeah, I have the Fourier transform of all experiments, but I took this, and you can see the similarity
Yes,
of
yes.
circle.
Okay, that's good. Now, okay, that's good.
I also tried this for rings,
Uh-huh.
and it got me this.
That's good.
It's almost like the hologram, I think.
Okay, now if
And
you
this
go
was the
one page up, there was a single ring
Yeah.
in the center. Can you go to some figures that we just showed to us? There was a
What?
single ring, you know.
Single ring.
Yes.
Yeah, this was the single
Oh,
ring.
yeah, yeah, yeah. So these, for example. Now, with our students, we have a European project where we are doing microscopy. And when we do microscopy, we do digital inline holography. This technique, we just use a laser, we use a pinhole, and we use cells. We have images of cells that we observe them. And these holography images that you have seen
Sorry,
so
I
far,
lost connection.
you lost connection?
Can you hear me?
Yeah, I can hear very
Yeah,
well. Yeah,
we hear.
you are good. But what I want to say is that in our group with other colleagues, we are doing microscopy, and in this microscopy, we take digital inline holography images using a laser, using the cellular material, and using a camera. The camera, it's a naked CCD, okay, or it's MOS, a complementary metal oxide detector. And these, what we are doing, we are magnifying the initial object, okay? So you have an object on the path of the light, which is a laser light in this case, and these obstacles, these targets which are dark or not 100% transparent, they behave like sources of light, okay? This is how diffraction happens. And this is what goes on in optics, okay? In optics, it's a similar object. So when you saw an equivalence between what you had calculated for holography and what you found for the Fourier transform of a shape, okay, it was a dark object, and that dark object, this is equivalent to some non-transparent object, okay. So in principle, in microscopy or
Professor, I have problem with internet connection. Sorry about the interruption.
yeah, we noticed that you just left and you were back, but for the other students that were listening, so especially this ring that we see here on the top at this moment on the slide, this is used, I mean, not this ring, but this targets which allow the light to pass only through a circular path. This is used in phase contrast microscopy. We are also doing this kind of imaging. Now, in this project, in this assignment or midterm project, you are just analyzing how the Fourier transform of images happens for different apertures. Okay, so maybe this is a very good keyword, so apertures. And in principle, in microscopy, you are using these concepts, but what we do in our techniques, in order to increase the spatial and frequency resolution, we call it spatial frequency resolution, we use a pinhole, we use a laser, and in the end, the images that we get, we try to remove the ripples. We try to remove these features which interfere with the correct image. Because in principle, imagine for a moment, you have a microscope, so which means that which you want to see two cells, which are next to each other. If you want to see them, they're going to interfere with each other with the ripples, the same way that we saw two particle interference or three particle interference, right? We all saw that. But we see them with this system, and we use a correcting algorithm or image reconstruction algorithm to remove the ripples, okay? And what remains, it is the magnified objects or the magnified cells or the magnified microscopic objects, okay? So now that you are specialists, Nicolina and Ernit, now that you are specialists of how the diffraction patterns develop or how imaging develops or how different sources of light behave, you might have a better understanding if you are one day, if you are assigned a task to do microscopy that uses digital inline holography or phase contrast microscopy, okay? But you know a little more now in terms of computational imaging. Computational imaging, it's a very modern research area, and very good researchers all around the world, especially in computer engineering and electronics engineering, they are doing all of these image reconstruction algorithms, which in principle, in its essence, somewhere the Fourier transform is there, okay? Because we can, to increase the resolution of a microscope, we can play around with the K-domain. K-domain is when we take the Fourier transform in X domain. So whenever we took Fourier transforms of these images here in this class, right, we are just going to the K space, okay? So we get the frequencies. If we take the inverse Fourier transform, we come back. If we can manipulate them back and forth, we are doing computational imaging, okay? Which produces very important and relevant outcomes. Okay, that was my final comment on this project.
Professor, this îmi face underpress. Am Clergon, Cadalini, Urgenți.
No, it's good.
Și Pușnuca prezentul.
Papa, mund të largohesh Erniti, të prezantimin tuaj tani we have recorded it. Shpresoj kurse ka dëgjuar tonë nga klasa mund ta dëgjojë më vonë, por mos u shqetëso Erniti, mund të largohesh. Unë falenderoj lutem Erniti.
Sukses e ju tjerëve.
Mirpafshim Erniti. The other students in the class will have a different session actually for their presentations, but for now we're just going to keep this much of the presentations. And meanwhile, actually, I'm thinking, let me think for a moment, we could go over a small exercise. When I say exercise, give me 1 second. Okay, then let's do it like this. I can use the next 10 to 15 minutes to see how we can use feature vectors to detect. Sorry. Sorry, I have an interference here. Okay, so I'll just spend a couple of. I can start sharing the monitor. Okay, now I'm set. I'll just present now let's see what we have here. Okay. Okay. Now, in terms of when we do the analysis of images, we have started with the, let me see, okay, I have to close something. We can often use different features. Now, the content that I can go over right now is from chapter 12 or 11 of the textbook. And we can see that we can associate different feature vectors or different metrics when we analyze a specific element in an image. An example here, we're going to see, let's assume for a moment that we want to read these images, or before we do that, let's clear some okay, this is gone, and let's say that we want to read these images. That's good. If you want to see how they look like, we have different shapes, out of which we have here they are. So we have a sphere, we have a square, we have like a droplet, and we have a six-sided star. And all of these images, they are on a black background. And what we can get from those, we can get different morphological parameters. Morphological parameters, it's a parameter which can relate to the perimeter of the object. It can be the area of an object. It can also be other parameters such as compactness, circularity, eccentricity. For example, eccentricity, we know that all the orbits of the planets in our solar system, they have a non-zero eccentricity, which means that they are not circular, but they move in elliptical paths, okay? So, which means that non-zero eccentricity. So we can quantify this one, and we can calculate what these values are. Now, those values that we just saw, give me a second, we can extract different, so for example, I1, it was a circle. So this circle, if you want to find the different parameters, let's see what we get. Okay, we get the compactness, which is around 10, circularity around 1.2, eccentricity 0.04. So eccentricity apparently is really small, and the reason is that this is coming out of a square. Okay, so this is these parameters. Let's see what is the second object. The second object, if we evaluate it here, the outputs, it will be that the compactness, it's not 10, but it's 42. Now we can write on the board all of these equations, and the compactness is defined as the perimeter square. Maybe better I can write here just for a moment. This is perimeter all square divided by the area. Okay, that's the compactness. Okay, and if you experiment a little bit with yourself, imagine that for a moment. Imagine that you have a pure circle, and then this circle you wiggle a little bit, so you add some interference patterns. The area is going to be the same, right? Because you just fluctuate on top of the circle. So let's assume for a moment, without passing to the, okay, I'm presenting the screen, I guess. So imagine for a moment that we have a circle like this, okay? And then on this circle, we change the circularity a little bit, and we make motions that go like this, okay? So you see, I just moved a little in and out, and compared to the more perfect circle, we have a new area which probably is equal to the previous area, okay? Because what we are taking out here, we are adding out here. So if the area is the same, we have that the perimeter, it has changed. Perimeter has increased. So if we have p squared over area, this new object, this will have a higher compactness, okay? Because this p squared is p increased, area is the same, good. So this is how these parameters we can define. Circularity is also a ratio between the area and the perimeter square. And let's have a look here. It looks like the compactness of the second object is much higher, which means that if this is the case, I'm talking about this 10 here and this 42 here, this means that this object, if it has the same area with the previous one, the second one has a higher perimeter. That's good. So similarly, we can have a look at the at the third object. And the third object, I3, let's see, it's not out yet. No, sorry, I'm just plotting it. No, this was wrong, but I have to show this, which means that these values now are 15 and 0.7. So circularity now, it's not a circle, it's closer to a circle than this one, but it's worse as a circle when compared to this other parameter, which circularity is 1.23. That's good. Now, this is how we can define certain morphological feature vectors or key elements to determine something about an object. Now, the thing is that how can we calculate these? In order to calculate these, what we can do is the following. So let's pick up, let's read again. Let's do this image prop. Let's do this clear all, and then we start from scratch. So we read an image, which is, let's see what this is. We read this image is 454 times 454. Let's evaluate. It looks like we have to close this. Sorry, figure 11. And let's see that this is, okay, this is the object, okay? It's a white object on a black background. And the maximum value here, if it's, let's see, what is the maximum value of the pixels for I1? It's 255. What we can do is that we can normalize this object, and the maximum value of this I, it was 255 before, okay? But now, after we scale it, the maximum value is 1, okay? And now what we can do is that we can, and let's have a look again at the figure. The figure is this one, okay? And we can identify, so now since we have also binarized this image, because it's 0 and 1, because it's 1 here and 0 everywhere, and now we can identify what are the coordinates of x and y where the intensity is 1, okay? So we can have here figure 111, histogram. Let's draw the histogram of this I, and here we are. We have just 0 and 1s, okay? And by the way, this histogram, I'm not sure if this can do this one in 2 classes. Okay, we did this in 2 classes, but we cannot see. So we have like 10 to the power 5 pixels. You should see the y value. They are in the value of 0. Let's zoom in a little bit here. No, sorry. Okay, so here we have the pixel which has a value of 0. Apparently we have 16 times 10 to the power 4, or 1.6 times 10 to the power 4. So around 16, they are here, and in white are a little less, apparently 4. So this is the histogram, but they are all 0 and 1s. That's good. We have binarized it. We identified where are the x and y. We can even have a look at what is this plot between x and y. It is predicted. It's just we plot x and y here, which is the mimic. It's mimicking this, okay? But let's not forget the image it was around 450 by 450. So here the radius is something less. It's in the order of 100. So this is where the 0s and 1s are. And now what we do next is that we have to calculate the covariant matrix. The covariant matrix, it's a matrix which tries to identify the major axis, okay? So let me say it in this way. If we have an ellipse and we calculate the covariant matrix, it's a matrix which multiplies the coordinates of x and y. But then if we have an ellipse and we calculate this, the major axis will be the direction of this ellipse, okay? So let's see that if we have this ellipse, we calculate the covariant matrix starting from the given coordinates, and we're going to identify these two x's. Okay, this will be, let's say, the output of the covariant matrix. That's good. So we just found x and y, which were equal to 1. Then we calculate the covariant matrix here, C. We evaluate this selection. Then we calculate the values. So C, matrix C, here it is. Okay, it's a 2 by 2 matrix. It's a 2 by 2 matrix because this covariant matrix, this is written. Let's not forget what this was. We used here. We have x and y. Let's see what is x. X is small value of x. They are all the coordinates here which show the that are 1, right? And what is important for us is to check what is the size of x. The size of x, it's composed of 45,000 and 45,000 different pixels, which are all ones. That's x. Y, it's a similar matrix, but then what we do is that this x and y, so we construct a new matrix A, which is equal to, we write this one x, y, and here we are, x and y, or you see how we constructed it? We just merged the coordinate of x and the coordinate of y, and this is what we got, and the size of A is this. The covariant matrix, it's calculated as we do the A transpose, right? We multiply this with A, and we divide this by a factor of n minus 1, okay? But if you do this, if you see, we get a 2 by 2 matrix. So covariant matrix, it's a 2 by 2 matrix, right? So imagine now we are trying to search if we have an ellipse where we're trying to determine what are the major axes. Now this matrix C, we calculated, it's here. We find the eigenvalues of this C, okay? Eigenvalues, if we see these values, they are really close to each other, okay? So it's like, let me see, you multiply by 10 to the power 3, this is 1, 2, 3, so this is 33,620.1, and the other component is 3,623.1, so they are relatively close to each other, which means that we don't have a perfect circle here, okay? It has some non-zero eccentricity. But, so, if, sorry, what did we calculate? We calculated the eigenvalues. That's good. So this is, after calculating the eigenvalues, we determine what is the maximum eigenvalue. The maximum eigenvalue, it's in fact the second value, right? So the bottom one. Okay. So L is equal to eigenvalues of C. Then we evaluate this value, which is predicted. So the maximum value is this one. The minimum value between the two eigenvalues of a covariant matrix is this new value. And then we use a code to determine what are the boundaries of this object. And the boundaries of this object is now, we can see it here as a variable, which is given here. Sorry, or it's a cell which is composed of 683.2, and it's a variable. It's a double. The variable type is double. Okay, sorry. And then we can determine this. If you read just the first coordinate of this BB, so this was the boundary of the object, this B, right? Now this BB is just reading the first column. The first column, or the first element, this is what the boundary is. And then this determines actually for a couple of steps in here, I could better use the board. But this P now, so this BB, it was finding the perimeter, or the coordinates of the X. Then once we find those, if we count those, that will be the perimeter, with the unit being a single pixel, okay? So now this P that we try to determine, apparently the perimeter is 683. And now 683, this is what we find. Let's divide this by 2 pi, by 2 divided by 3.14. It looks like the radius is around 108, and that's what it is actually. So then we can determine what is the area. Okay. Then after we get this area, we calculate the compactness. Okay, what is the compactness? It's equal to p perimeter square over the area. Then we can calculate the circularity, how much of a circle it is. We calculate it like this, and actually, let me remove this for a moment, and these here. So compactness, it was a circle, it's like 10.17. The circularity, actually we calculated this one, so that's why we get this 1.23. And eccentricity, since our object, it looks very close to a perfect circle, eccentricity is going to be a small value, okay? And as a mathematical, so it's like 0.04, it's almost zero. Actually, the eccentricity of planet Earth, it's, I guess, it's 10 times smaller than this. So planet Earth, we are pretty close to a circle. Our orbit, when we circulate, when we come across when we orbit around the sun, I guess our eccentricity of Earth is 10 times smaller than this circuit. So we are not, as a planet, we are doing a good job. But then, so this is how these parameters we can determine, okay? So these are the formulas. So this is how we did it. The only trick or careful step is the following. We determine the location, the coordinates of regions of interest, which in this case are ones, because we are identifying an object as white on a black background. Then from these coordinates, we calculate the covariant matrix, okay? And the covariant matrix, if the initial our coordinates initially, it was 2 by 1. We had a matrix which was 2 by 1, okay? It was 2 by 1. But now, imagine now, if you have a matrix which is 3 by 5. So let's say we have a matrix which is random integers, which is here, let's see what we get, 3 by 5. Okay, we have a matrix 3 by 5. The next question that comes to our mind, and I'm going a couple of steps backwards to understand the code, we calculate the covariant matrix, which is going to be A transpose times A. So it's going to be a matrix which is, let's see what is the size of this answer. It's 5 by 5. So the covariant matrix is going to be matrix 5 by 5. That's good. The x and y coordinates for the object that we just analyzed, it was 2 by 641, whatever the length was. When we multiply the transpose with the original matrix, we get a covariant matrix which is 2 by 2. And then for this covariant matrix, we find the eigenvalues. And if the eigenvalues are equal to each other, we have a perfect circle. Okay? If the eigenvalues are different from each other, then that means that we have some degree of non-circularity. Okay? So with these detailed steps that we did in this part, or that we wrote the formulas ourselves, these formulas were used to get these values, which I guess we found them. Wait a second. So let's go back for a moment. So we calculated, we read these 4 different images. When we plot them, they look like this. And then from here, we could calculate all the parameters of interest, which would be these values, and the output would be shown here. No, okay, so here we are for all the parameters. We have some I5 BZ, then let me see. Okay, close all, clear all. Let's read this other image. So let's see, I5. We read an image which is I5, and let's see what it is. I5, we get here im show I5. Here we are. Okay, we have a series of different objects. Okay, and this I5, we have a look at the data. It's a 1500 by 1600 by 3. Okay, which is RGB apparently. So first of all, let's convert this one to a grayscale. We use this code here. Now, if you look at the variable, it changed. It's not by 3, but it's 1500 by 1600 alone, unsigned integer 8. And we can resize this down to make this a little smaller by a factor of 2. And we get here half of what it was. And then we can have a look at the max of I5. What is the maximum value? Is 255. That's good. We can binarize this. And if we binarize this, the maximum value, okay, no, it should be I5B. It's 1. So now we binarize it. So let's see. We had an image which was I5. We converted it in grayscale. We resized it. We made it smaller by a factor of 2. Then we binarize it. The variable is called now I5B binarized. Okay. And this I5B binarized, let's have this figure 4. This is how it's going to look. Evaluate selection. Okay. Now here, so this is, they are still the same actually. We don't see a big difference, but we want to have the black background and white object, okay? Because when we calculate the boundary, we want to have the object in ones and the background in zeros. And for this, we just do this make background 0, I5 binarized with a B and background 0 with a Z. We find it like this. And this figure, which we can denote this figure 6, we can see how this is going to be. And different from these, we have the objects which are ones in a black or background. So it's the negative of the original image. And now that we have this, we can try to find what are the parameters. And the parameters is going to be a little confusing because we have several objects which are in there. So that's what we see. The compactness is a small value because we had a high compactness for circles, but now this is like a mixture of everything, so it's slightly different. And we can also try to crop out a smaller region. So we just pick up, let's evaluate this. We cropped out from this original image, which is shown here, we just crop the top part, which is a square, okay, it's just this one. And from this part, we can find I5 prop. This IS, it means small I, okay, small image. And we can find, again, morphological features, which are given by these numbers. And it looks like the compactness of a single square is a little higher. So we can go a little more practice, but this is some important part when we analyze the morphology of different objects. Now, in different imaging, in different areas of research, often when we compare different objects, comparing circularity, eccentricity, and compactness are important parameters. We need to use those. And by the way, okay, for a moment I thought, I was afraid that my microphone was off. So this is all I can stop for now. I think we can give a break for today. Do you have any question?